Testing. 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 All right. Good. Okay. Up here. Alrighty, welcome to another Hoopo stream here. Hope you guys had a good weekend. Today we're going to start the week off with this blog article here, part of the Google Research blog page. This is written by Jeff Dean. So Jeff Dean is kind of legendary computer science, legendary engineer. And I think he mostly kind of runs Google Research now. Maybe it's more of a ceremonial role. I don't exactly know how much management he's doing, but he's a very good engineer. He has a good kind of idea of the trends that kind of drive, and he has these blog posts that he does basically roughly every year where he kind of summarizes what happened in AI during the past year and kind of where he thinks AI is going. And yeah, they're usually pretty interesting, usually well written, good figures, and so on. Usually they kind of let you peek at what Google Research is working on. Obviously, there's a little bit of bias where he always kind of makes it seem like Google's the only one that's doing anything important. But, like, for example, I doubt he mentions ChatGPT in here. But I think they're always interesting and they're always a good read. So we're going to go ahead and read these. So go ahead. Today we kick off a series about exciting new developments. Please keep your eyes on this space. I've always been interested in computers because of their ability to help people better understand the world. Okay, much of the research has been in pursuit of a similar version. To better help people better understand the world and get things done. So you kind of see actually a fundamental change in the way that the Google mission is listed. I feel like the original wording is more help people access the world's information, but now it's get things done, right? So kind of as we move into the age of kind of AI, it seems like Google's kind of changing the messaging around its mission, or at least the wording, to reflect kind of the capabilities. Complex information-seeking tasks, creative tasks, analysis and synthesis tasks, partnering with people to jointly to write software together. We want to solve complex mathematical or scientific problems, transform modalities, translate the world's information into any language, diagnose complex disease, understand the physical world, accomplish complex multi-step actions in both the virtual software world and the physical world of robotics. I think physical world of robotics is a key one there, right? As you guys saw in the earlier stream we did there, Google's putting a lot of effort into kind of embodied intelligence, right? This idea of taking all the advancements that have happened in AI and trying to put them in a kind of robot that you could put in your house, you can put factory, and so on. The kind of huge allure of a market of the kind of general purpose robotics market is a trophy that all the big tech companies want to get. We've demonstrated early versions of some of these capabilities in research artifacts. We've partnered with many teams across Google, blah, blah, blah. This post, I'm kicking off a series, highlight some exciting progress, and present our vision for 2020. Language, computer vision, multimodality, and generative learning models. And yeah, he's going to have more stuff. Okay, so he has a couple articles in this series, I guess. So he has one specifically computer vision for language models, multimodal models. Actually like oh, okay, this is just like an index. Okay, so this is the table of contents. Control 2, Control W. Right, so okay, language models. Progress on larger, more powerful language models has been one of the most exciting areas. Important advances such as sequence-to-sequence learning and our development of the transformer model underlies most of the advances in this space in the last few years. Although language models are trained on surprisingly simple objectives like predicting the next token in a sequence of text, when large models are trained on sufficiently large and diverse corpora of text, the models can generate content, blah, blah, blah. Yeah, so, I mean, I think there's a lot of people within the machine learning community that think that at the end of the day, the only thing that matters is kind of having a huge data set and the actual algorithm is irrelevant. And, right, that's kind of the ideas behind the bitter lesson by the Sutton that we were looking at last week. I'm definitely of that opinion that I think that too many people put emphasis on the algorithms, right? The transformer, right? That's really what it was. But no, the reality is it's really just the ability to train in a massively parallel way and to have a huge amount of data to train on. That is, at the end of the day, what is driving progress in AI and large language models. Okay. Our ongoing work on Lambda explores how these models can be used for safe, grounded, high-quality dialogue to enable textual multi-turn conversations. Okay, so I guess this is back and forth, like you say something, the AI says something, you say something, the AI says something. Natural conversations are clearly an important way. Rather than forcing ourselves to interact in ways that best accommodate the limitations of computers, we can instead have a natural conversation. Excited about the progress. Described our work on Palm, a large 540 billion parameter language model built using our pathways and trained on TPUs. So Palm is basically the ChatGPT, is kind of like the large generic LLM trained on like a masking task on a, right, solely on the objective predicting the next token. It's not masking. Masking is more you blank out certain words in a sentence and you try to predict those words. This is you mask out the last word in the sentence and you try to predict that last word. Large-scale language models trained on large amounts of multilingual data and source code are capable of improving state-of-the-art across a wide variety of natural language translation and coding tasks. Works provided additional evidence that increasing the scale of the model and training data can significantly improve. Okay, Palm 540B. So what is this? You have performance comparison of the Palm LLM and the prior state-of-the-art on 58 tasks. So preferred metric delta. Okay, it's a very generic y-axis. I have no idea what that means. It just means the delta between a metric. They don't tell you, so I have no idea what the scale of that is. But basically what they're showing you here is that Palm performs better than this prior state-of-the-art. There's only a small amount of tasks here where the prior state-of-the-art performs. We have seen significant success in LLMs using a variety of code completion suggestions from 500 million parameter language model for a cohort of software developers. We've seen that 2.6% of all code comes from suggestions generated by the model, reducing coding iteration time by 6%. Yeah, this is huge. I mean, as you guys see on this channel, I use kind of code completion all the time. That code, Microsoft ChatGPT. Yes, or the other way around. There will be an of AI GPT, which is Microsoft. Probably. Yeah, so there's not going to be one giant AI company. I think that already you're having multiple different of the big tech companies that can compete in this space. Google, Microsoft through GPT and OpenAI. Meta, and then probably one or two of the Chinese companies will also have their version as well. But yeah, I don't think any one of them is going to win right now. If there's a winner, it'll be kind of in the future for some reason that we don't really know. TikTok, maybe. Lol, maybe. Is TikTok owned by parent company? Lots of money. Okay, one of the broad key challenges is to build systems that can perform multi-step reasoning, learning to break down complex problems into smaller tasks and combining solutions. A recent work on chain of thought prompting, whereby the model is encouraged to show its work into solving a new problem, helps language models follow a logical chain of thought and generate more structured, organized, and accurate responses. Yeah, so this is very interesting stuff too, where whenever you're talking to ChatGPT, if in your prompt you ask it things like show your work or do it step by step, right? There's like kind of like these phrases that you can put into ChatGPT that force it to like be a little bit more logical and a little bit more step by step. And that's called chain of thought prompting. They probably have a blog post for this. But yeah, for example, here's a good example. Actually, they probably have this. There you go. I was going to say, all right, they have this exact same picture here. So in standard prompting, if you kind of ask this large language model, this isn't ChatGPT, this is kind of Palm, which is basically just the Google version of it. If you ask it the question directly, it's going to kind of get the answer wrong, right? It's kind of, you're asking the question in a very compressed way, right? But in chain of thought prompting, right, rather than saying the answer is 11, you kind of you show the model that you want it to show its work, right? You want it to say, you don't want it to say the answer is 11. You want it to say Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 equals 11. The answer is 11, right? And when you force the LLM to kind of do the same sequential kind of thinking, it ends up getting the right answer, right? So you can see here how if it's told to just give you the answer immediately, the answer is usually wrong, but if it's told to kind of show its work, the answer is actually right. So chain of thought reasoning, I would say this kind of falls into kind of prompt engineering, right? Which I think is going to be more and more of a thing where you need to know how to type your questions to these large language models to get the right answer. And if you don't do it, you might actually get a wrong answer. The ability of models to solve complex mathematical reasoning and scientific problems. The research question is whether ML models can learn to solve complex problems using step reasoning. By taking the general purpose Palm language model and fine-tuning it on a large corpus of mathematical documents and scientific research papers from arXiv, and then using chain of thought prompting and self-consistency decoding, the Minerva effort was able to demonstrate substantial improvements on state-of-the-art for mathematical reasoning and scientific problem. Okay, so it looks like they basically took the giant LLM, fine-tuned it on all the papers on arXiv, and it quite good at these benchmarks here. MMLU STEM, I think these are just basically question-answer benchmarks, and you can see how the performance jump here is pretty huge, from 6.9% to 50%, 55 to 75, so these big LLMs are making huge jumps in kind of the benchmarks for reasoning. So we're having kind of a similar moment to the AlexNet kind of computer vision moment that was in 2012, 2013, but now it's kind of on logical reasoning data sets, or logical reasoning benchmarks. Chain of thought prompting is a better way of expressing natural language prompts and examples to a model, improve its ability to tackle new tasks. Similar learned prompt tuning, in which a large language model is fine-tuned, has shown great promise. Large language models include clinical knowledge. We demonstrated that learned prompt tuning can adapt general-purpose language model to the medical domain with only a relatively few examples that the resulting model can achieve. Okay, MedQA, U.S. medical license exam, 67% accuracy. Whereas the previous state-of-the-art on this MedQA was 17%. So that is absolutely massive, right? It's going from basically guessing, I guess, right, like 1 in 4 to 67%, which is almost a C grade. So huge jumps in performance. Suggesting the potential utility of LLMs in medicine. Large language models trained on multiple languages can also help with translation. Traditional machine translations. However, since parallel text exists for relatively small languages, many languages are often not supported. Okay, so there's been a couple papers here that Google's published where they have a set of techniques that use massive multilingual language models trained on monolingual non-parallel datasets. So yeah, it seems like basically the way that translator AIs were trained before, you need to have this like one-to-one, like this paragraph in French is equivalent to this paragraph in English, which you can almost think of analogous as supervised training, right? Where you're basically have a very painfully labeled supervised data set where you have kind of like, this is the input, this is the output. And it seems like people have figured out how to do language translation without that, right? They have an unsupervised data set now. They call it monolingual data set, but it's basically the same thing as going from supervised training to unsupervised training. So this is a pattern that you're seeing across a bunch of different AI disciplines where if you can figure out how to use unsupervised training, you're going to be able to train on way more data, which means you're going to get way better results than having some kind of supervised training objective. IBM. TikTok owned by IBM? By TikTok, one in China as Douyin developers, ByteDance. ByteDance. ByteDance is financially backed by SoftBank, Sequoia Capital, Hillhouse. Okay, so it's not owned by any of the big Chinese tech companies, but they do have basically like kind of generic VCs here. Headquarters, China, but legal domicile, Cayman Islands. So sketch. Another approach is represented with learn soft prompts, where instead of constructing new input tokens to represent a prompt, we add a small number of tunable parameters per task that can be learned from a few task examples. This approach generally yields high performance in which we have learned soft prompts while allowing the pre-language model to be saved, shared across thousands of different tasks. Okay, so basically kind of a little bit of fine-tuning, right? Except here they're calling it task adaptation. Okay. As the scale increases, prompt tuning, which conditions frozen models using tunable soft prompts, matches the performance of model tuning. Yeah, so in model tuning, what that means is that you're pushing gradients, right? You have your big model that's been trained on some kind of unsupervised next token prediction or mask token prediction. And then you have a application-specific or task-specific data set, and you're running a couple epochs on that task-specific data set and pushing those gradients with a small learning rate into your big model. And now your model is kind of fine-tuned or tuned for that specific task. But what they're finding now is that you don't actually need to do that. You can actually just, as part of the prompt, you kind of show a couple examples of what you want, right? So you're fine-tuning the model without pushing gradients by just engineering the prompt, right? That's what they're calling here prompt design. So we're seeing that as the number of model parameters gets higher and higher and higher, you no longer need to fine-tune these models for specific tasks. All you do is just prompt them in a specific way, and the big model can adapt. So I think this is huge because I think you see this in large language models, but you still don't see this in computer vision. I think in computer vision, we're still very much in this model tuning paradigm where if you want to use a computer vision model for some application, you're going to basically fine tune a big computer vision model for your application. But I think eventually there'll be a way to kind of prompt a computer vision model such that you never need to fine tune it on your application specific things. The utility of language models can grow significantly as their size increases. Characterizing emergent phenomena in large language models examines the sometimes surprising characteristics that these models are not able to perform particularly complex tasks until very effectively until reaching a certain scale. Okay, so yeah, this is an interesting part too. Sometimes this is called emergent behaviors, but basically what this is showing you is that the model performance is not linear over time, right? Where it's like here on the x-axis, you have the size of the model, right? Roughly. That's basically here they have training. So it's basically like how long are you training these models for, which is a rough proxy for how much data has it seen. And you would think that it would kind of be linear, right? The more you train it, it kind of gets smarter and smarter and smarter and smarter and smarter, and then it keeps going up. But that's not actually what you see. What you see is that for a long time, it doesn't actually go anywhere. It's not getting any smarter. It's the same. And then suddenly you get to this point, and then it gets really smart really quick. So there's kind of this non-linear nature, like a step function nature to the actual performance of a model on a task. So the interesting thing to that is what happened, right? What happened between 10 to the 20th and 10 to the 22nd here? Like why is there suddenly this huge jump in performance? And you can kind of anthropomorphize and think about like, okay, well, does that mean, is that kind of what humans are doing, right? When you're a human and you're trying to learn something, like you kind of don't really know what's going on, and then finally it kind of clicks in your head, and then you're like, oh, and then you understand what it means, and then you now suddenly learn. So you're seeing a kind of similar-ish behavior in these AIs where it's like there's kind of like a moment where it clicks. As these models continue to improve and become more sophisticated, they will likely play an increasingly important role in many aspects of our lives. Yeah, I think this is the most interesting part. Like, we're living in the most interesting decade of human development. I think that the 2020s to 2030s is where AGI will cross the human intelligence, right? Like, there's a point where the AIs are just going to, as soon as they become more intelligent than humans, and I think we're like literally right there. I think like 2023, 2024, that's going to be the point. Suddenly everything changes, right? Every single business model has to be reevaluated, kind of our relationship with society, our relationship with jobs and work, all of that changes. So it's a very interesting time to be alive for sure. All right, let's get to computer vision. Let's go. Computer vision is more my thing. I am not a LLM guy. I'm not really, but computer vision is my jam. So let's get in here. Boo, you have something to say? Come here, Boo. Boo, you want to say hi to the stream? Want to say something? All right. Computer vision continues to evolve and make rapid progress. One trend that started with our work on vision transformers in 2020. Did they start it? I feel like Facebook started it. Maybe it was Google. Damn, okay, maybe I did that wrong. I thought that it was Meta or Facebook that actually had the first vision transformer paper, but it seems like they're trying to claim that Google had it. I don't know. Who cares, right? But yeah, basically transformers have penetrated computer vision. So computer vision models almost always were convnets, and then now a lot of people are basically using VITs, as they call them, vision transformers, which is basically cutting up an image into little patches and then feeding in those patches as if they were words in a sentence. Although the localized feature building abstraction of convolutions is a strong approach for many computer vision problems, it is not as flexible as the general attention mechanism in transformers. which can utilize both local and non-local information about the image throughout the model. However, the full attention mechanism is challenging to apply since it scales quadratically with image size. Yeah, this is the rub with transformers, right? Where because in a transformer, what it's fundamentally doing is it's kind of multiplying every element of the sequence with every other element of the sequence, right? That's what attention means. It's like every part of the sequence can pay attention to any other part of the sequence. Means that the sequence length or the image size, if you're using images, it's going to scale quadratically with that, right? Whatever the size of that rectangle is, the bigger you make the length of that square, the area of the square squares. Okay. So in MaxVIT, multi-axis vision transformer, we explore an approach that combines local and non-local information, but scales more efficiently than the full attention mechanism. Okay, so they have some work where they try to remove this kind of quadratic scaling. This approach outperforms state-of-the-art models on the ImageNet 1K and various object detection tasks. Okay, in MaxVIT, multi-axis attention mechanism conducts a blocked, local, and dilated global attention, sequentially followed by a FFN with only linear complexity. I think FFN here means feed-forward network, so just basically a bunch of neurons all connected to each other. The pixels in the same color are attended together. Okay, so block attention here, I guess, is you have these 4 blocks where you only do attention within here. So rather than having an 8x8, right, which is 8x8, 64, you have 4x4, which is 16, and then you probably do all 4 of them together. So it's like one batch of 4x4s rather than a batch of 8x8. So there's probably memory efficiency by doing it by kind of cutting it into these little blocks and then doing it in parallel. And then here you have this what's called like dilated, right? So dilated is dilated convolution. This is like a kind of a normal convolution here, and then this is a dilated convolution, right? Where the dilation refers to like how far is it spread, right? A good picture. So in convolution, it's like kind of packed, dilated, separated out like that, right? So here you have dilated global attention. So here you have local block attention where each block is separated locally. And then you have here a dilated global attention where all the blocks are dilated, but then done together in an 8x8, so it's global. So maybe we read this paper. That sounds kind of interesting. When was this paper published? September 8th. Yeah, this actually sounds kind of cool. Look at that. Okay, so in Pix2Seek, a language modeling framework for object detection, we explore a simple and generic method that tackles object detection from a completely different perspective. Unlike existing approaches that are task-specific, cast object detection as language modeling task conditioned on the observed input pixels with the model trained to read out the locations and other attributes of the object. Okay, so you're seeing more and more of these kind of approaches where rather than coming up with some specific computer vision problem formulation and then having to come up with a supervised training data set for that specific thing, people are trying to use these large language models as much as possible. So here, even though, right, you have this picture of the swans and they're trying to make it a language task where basically you take your LLM and you tell it to output the coordinates, right? So this is almost like a form of prompt engineering, right? Where basically you're saying, I'm going to give it the first part of this and then it'll complete the rest of it. Maybe they don't exactly use the LLM here, but like the idea of like using language as a core part of computer vision models is only really an idea now because language models are so huge, right? Like 10 years ago, you wouldn't want to use language models in computer vision because the language models were crap anyways, right? So now language models are so good that people are trying to figure out ways to use them for things like computers. Another long-standing challenge is to better understand the 3D structure of real-world objects. Yeah, so going from 3D to, or 2D to 3D. We have been trying multiple approaches. In large motion frame interpolation, we demonstrated that short, slow motion videos can be created by interpolating between pictures that were taken seconds apart. In view synthesis with transformers, we show how to combine two new techniques, light field neural rendering and generalizable patch-based neural rendering. So neural rendering just basically means creating new images with a neural net, right? And there's a bunch of different types of neural rendering, and you guys are probably familiar with ray-based neural rendering, right? What's sometimes called neural radiance fields, which is a type of neural rendering. So these are different types of neural rendering here, light field and generalizable patch-based neural rendering. LFNR is a technique that can accurately reproduce view-dependent effects by using transformers that learn to combine reference pixel colors. While LFNR works well on single scenes, its ability to generalize to novel scenes is limited. Yeah, this is true. Like most neural rendering techniques, they're trained on like a specific scene, and it's usually a static scene. So we read a paper earlier last week, I think, where we were looking at neural rendering for dynamic scenes, but that's still kind of on the bleeding edge of research. So here in this figure, they show you how just from some images of this scene, right, these 4 images here, you can feed these into these neural rendering models that they're not generic. They're trained specifically on this scene, but it's impressive that it can create this smooth video, and most impressively is kind of the fact that these test tubes have all this kind of like refraction and like weird lighting and colors, and it's semi-transparent. So that's the impressive part here. Okay, going even further, LolNerf, learn from one look. We explore the ability to generate high-quality representation image. Okay, so there's a cool Nerf paper. Okay. That's probably another paper we can read, but this is basically a Nerf that's just one image. So you make a Nerf from a single image. Look at these nice little cats here. We can learn through the expected 3D structure to create a 3D model from just a single image of a novel category. General thrust of this work is to develop techniques that help computers have a better understanding. Okay. All right, so that does it for computer vision. The next section here is about multimodal models, right? Modalities is basically, here you go, single modality of data such as language, image, or speech. And multimodal models are models where you try to use multiple modalities, right? Text and image, speech and language, and so on. As we look forward to multimodal data models, handle many different modalities, both as model inputs and model outputs. Yeah, and one way to think about the advantage of multiple modalities is that you're just increasing the size of the data you have available, right? If you're only limited to image data, your data set is going to be smaller than if you can use image and text data. So like part of the whole point of using the same model, of having the same model be able to use text and image, means that your data set size can increase, right? And I think that that's something you're going to see. I think in the future, right, we're already kind of running out of data. You're kind of, if you train GPT-4 on the entire internet, like where else are you going to get more text, right? That's kind of all the text that exists. So in order to get an extra huge amount of data, what you're going to have to do is you're going to have to start using videos and image as well. So like to keep 10xing the size of the data, you're going to have to start having more and more different modalities. Okay, there are 2 key questions when building a multimodal model that must be addressed. How much modality-specific processing should be done before allowing the learned representations to be merged? What is the most effective way to mix these representations? In our work on multimodal bottleneck transformers and the accompanying attention bottlenecks for multimodal fusion, we explore these trade-offs and find that bringing together modalities after a few layers of modality-specific processing and then mixing the features from different modalities through a bottleneck layer is more effective than other techniques. This approach substantially improves accuracy on video classification. Okay. So a bottleneck, right, is the neck of a bottle, which is kind of in most bottles there's this kind of choke point, right? There's kind of neck to the bottle. And bottleneck in the context of a neural network refers to kind of like a point where rather than having the same width in a layer, right, where you have 10 here you have 4 neurons, 4 neurons, 4 neurons, 4 neurons, 4 neurons, like what you can do is actually create this like choke point where now the information has to go from 4 neurons to 2 neurons and then back to 4 neurons, right? UNets kind of use this as well. But partly what's happening here is that you're forcing your neural net to like compress the information into a lower dimensional space. And when you compress the information into that lower dimensional space, the neural net is forced to learn a more compressed representation of the knowledge, right? And that compressed representation of the knowledge is more useful for prediction, which is largely just interpolating in this compressed dimensional space. So there is some like theory there about like how do neural networks learn, and part of the arguments that people say is like it's because you're kind of have these choke points where you're forcing the neural net to like learn and shape a manifold in this lower dimensional space. Typical approaches to fusion of multimodal transformer encoder features use pairwise self-attention across hidden units. Bottleneck fusion restricts attention flow within a layer through tight latent units called attention bottlenecks. Bottleneck mid-fusion applies bottleneck fusion only to later layers for optimal performance. Okay. Combining modalities can often improve accuracy on even single modality tasks. This is an area we have been exploring for many years, including our work on Device, which combines image representations and word embedding representations to improve image classification accuracy, even on unseen object categories. A modern variant of this general idea is found in locked image tuning, LIT, a method that adds language understanding to a pre-existing pre-trained image model. This approach contrastively trains the text encoder to match image representations from a powerful pre-trained image encoder. So this is kind of contrastive image language pre-training, which is basically what CLIP is, right? CLIP, which is a model from OpenAI, does the same thing, right? Where it's kind of forcing the text embeddings and the image embeddings to kind of get closer together, right? So this is really just CLIP, right? They're calling it LIT, locked image tuning, but it's basically the same thing. It's you feeding these images that have a corresponding text, right? And the pre-trained image encoder is going to take that image, turn it into some kind of embedding, and it's going to take the text and turn it into some kind of embedding. And then you want to create a loss that makes those two embeddings as close as possible. So either you're pushing gradients into the image encoder, or you're pushing gradients into the text encoder, or you're pushing images or gradients into both of them. But that idea of like moving embeddings in a space together is called contrastive learning, and doing it with images and text is the whole contrastive language and image training, but here they're calling it locked image. Another example of unimodal utility of multimodal models is observed when co-training on related modalities like imaging and videos. In this case, one can often improve accuracy on video action classification tasks compared to training on video data alone. Yeah, there's more signal, right? So the more modalities you have, the bigger your data set can be, and the more signal there is to learn something, right? Combining language with other modalities is a natural step for improving how users interact with computers. Yeah. combining language and vision. So here they have PALI, scaling language image learning. They have over 100 languages. Right, so the encoders that they're using for images now, for example, this pre-trained image encoder, I don't know in this paper, in the locked image tuning, it might be a ConvNet, but ideally we're moving into a world where even the image encoder is entirely transformer based with vision transformer. PALI achieves state-of-the-art results on cross-modal 3600 benchmark, a diverse set of multilingual multimodal capabilities. As the figure below shows, having a single model that can simultaneously understand multiple modalities and many languages can do tasks. Yeah, this is the future here. Computer systems where you can have a natural conversation about other things, other kinds of sensory inputs, such as asking questions and getting answers to your needs in a wide variety of language. How many parakeets do you see sitting on these images? Describe this image in Swahili. So this is PALI. Our work on Find It enables natural language questions about visual images to be answered through a unified, general-purpose, and multitask visual grounding model that can flexibly answer different types of grounding and basically you can go from a text query into detection. The area of video question answering, given a banking video, being able to answer a question like, what is the second ingredient, requires the ability to comprehend both text inputs and video inputs to produce a text answer. In efficient video text learning, video inputs are versions of the same video input are efficiently fused together with the text input to produce a text-based answer by the decoder. Instead of processing the inputs directly, the video text iterative co-tokenization model, co-tokenization, so it's tokenizing the text and the image at the same time, I would suppose. That's what that means. Learns a reduced number of used tokens from a fused video language inputs. This process is done iteratively, allowing the current feature tokenization to affect the selection of tokens at the next iteration. Yeah, so this is almost like a recurrent kind of architecture here, where the future inferences are not only given the inputs of the current step, but they're also given some kind of embedding from the previous step. What is the second ingredient important to the process of creating high-quality video content often includes several stages, from video capturing to audio editing. In some cases, dialogue is reordered in a studio to achieve high quality and replace original audio that might have been recorded in noisy or other suboptimal. However, the dialogue replacement process can be difficult and tedious because the newly recorded audio needs to be well synced, often requiring several edits to match the exact timing of mouth movement. So this kind of tries to match it more. Or a multimodal model for accomplishing this task more easily in visually driven text-to-speech. The model can generate speech output of the text that matches the video while also recovering aspects of prosody. This. In linguistics, prosody is concerned, or prosody is concerned with the elements of speech that are not individual phonetic segments but are properties of the syllable and larger units. Okay, so it's basically intonation, like rhythm and intonation. I don't think the audio is set up, so you guys probably can't. In Look and Talk paper, we show how on-device multimodal model and use both video and audio input to make interacting with Google Assistant natural. So the impressive part here is that you're running a multimodal model on device, right? So multimodal models, right? Every additional input modality will require usually a kind of a different encoder. And if you have an image encoder and a language encoder, that can be a lot of computation, right? The size of that model gets pretty big. So the fact that they're doing this on device, on like one of those little like Google Homes, is quite impressive. It's probably a heavily kind of quantized and a lot of sparsity within that model, but it's still impressive that you can do multimodal on-device models. The model learns to use a number of visual and auditory cues such as gaze direction, proximity face matching, voice matching, and intent to more accurately determine if a nearby person is actually trying to talk to the Google device. Or merely happens to be talking near the device without the intent of causing the device to take action. Multimodal models don't have to be limited to just combining human-oriented modalities like imagery, and they are increasingly important for real-world autonomous vehicle and robotic applications. In this context, such models can take the raw output of sensors that are unlike any human senses, such as 3D point clouds, data from LiDAR units, combine this with data from sensors. Okay, so I think in all the previous paragraphs, they were talking about multiple modality, mostly in the context of text and image, or text and video, which is just the same thing as text and image. But obviously, Google does a bunch of autonomous vehicle stuff, and Google's autonomous vehicles are use a lot of LiDAR, right? So like on the top of a Google autonomous car, right, you have this this little bump here at the top. This is a LiDAR unit, right? So it's basically shooting out a bunch of little lasers and then getting a bunch of points in the world, right? That's what the point clouds are, right? So you see how it has this kind of like 3D representation of the world. So feeding that weird 3D representation of the world, which is like a collection of 3D points, is kind of a weird kind of modality to feed into a neural net. So there's different ways of feeding it, and one of the ways that people do it is they turn it into like a image, right? So here they're calling it pseudo image. And here you see a kind of fusion happening where the pseudo image is getting fed into a convnet at the same time as the 2D images from just like the color camera on that car, right? And by fusing these, they can get a better estimate of the different objects in the scene. I think that an opinion that a lot of people have in robotics and kind of autonomous vehicles, and that Tesla is famous for kind of being all in on this approach, is that you don't actually need these LiDARs, right? These LiDARs are actually, they're expensive, they add all this extra complexity, and you might not even need them, right? So you're actually just better off putting more cameras. Just take that $100,000 LiDAR, and instead of spending $100,000 on one LiDAR that you put at the top of your car, just put 10 more cameras around your car. That'll cost you $1,000, and from 40 cameras all around your car, you're going to get better autonomous vehicle than 10 cameras around your car and a $100,000 LiDAR on top. So kind of my low-key prediction is that these LiDARs eventually go away and everything is just camera-based, but I think the big LiDAR lobbyists will figure out a way to keep the LiDAR in the game. Having single models that understand many different modalities fluidly and contextually, and that can generate many different kinds of outputs in that context, is a much more useful and general purpose framing of thing. We're excited about where this will take us because it will enable exciting new applications of many Google products and also advance the fields of health, science, creativity, products, and more. So interestingly here, they keep mentioning health, right? They mentioned it at the top and then they mention it here. So I feel like maybe Jeff Dean here is kind of like conditioning us to the reality that Google is going to try to enter the healthcare market, right? Specifically some kind of like general purpose, like ChatGPT type thing that kind of you ask it medical questions and it gives you responses, because that's a huge market, right? The medical market is huge. So it seems like they're hinting at some kind of product in that space. Okay. So the next section here is diffusion or generative models, and then we have generative audio, and then we have a responsible AI. Okay, so the next section here is going to be about generative models. So quality and capabilities of generative models for imagery, video, and audio has shown truly stunning and extraordinary advances in 2022. Yeah, I would say 2022 is like the year of the generative image models. There are a wide variety of approaches for generative models, which must learn to model complex data sets. Generative adversarial networks, right, made by Ian Goodfellow, and this is quite old now, in 2014, set up two models, right? You had the generator and then you had the discriminator kind of fight against each other, and basically over time the generator gets better and better at creating images that look like the real data set. You see here, this is what in 2014 GANs were capable of. It's kind of like grainy faces. And you can see over the years they've kind of gotten better, higher resolution, more diverse data. But GANs were always very tricky to train, and they kind of had their problems with training, and kind of the adversarial aspect made them difficult. But in 2022, the way that people are generating images is not with GANs anymore. It's right with these diffusion models. And these seem to work much better. They're much more stable to train, and you've kind of seen an explosion of different companies and different models that have used diffusion models. Diffusion models, introduced in deep unsupervised learning using non-equilibrium thermodynamics in 2015, systematically and slowly destroy structure through an iterative forward diffusion process. They then learn a reverse diffusion process that can restore the structure, the data that has been lost. The forward process can be used to generate noisy starting points for the reverse diffusion process conditioned on various useful controllable inputs to the model, so that the reverse diffusion process becomes controllable. Yeah, so basically these diffusion models, they learn, you add noise and then they remove the noise in training. That's basically kind of the unsupervised task that you're doing. And then you can, in inference, just ask the model to remove the noise when you don't actually know what the noise is, and it'll produce that image for you. So you see here over time, right? What the when you're performing inference, what it's going is going from basically this to this. It's each step removes noise, and there can be thousands of steps. And then we've also seen papers where people do it in one step. And when you train this model, you're kind of going backwards, right? You start from a picture and then you kind of add noise. Various forms of autoregressive models have also been applied to the task of image generation. So in 2016, you have Pixel RNN, okay, which is a recurrent architecture, and Pixel CNN with the ConvNet. And then VQVAE, right, the vector quantized variational autoencoder. Yep, vector quantized variational autoencoder. So to the point on kind of this choke point here, right? This stuff that they were doing here, right? The bottleneck. The VQVAEs also kind of work on this idea of bottlenecks, right? Where autoencoders try to compress the information down to this like smaller code book of vectors, right? Those quantized vectors, vector quantized. And then by compressing the information into this lower dimensional vector, the model kind of learns a manifold in that lower dimensional space that kind of represents your data. And we saw how actually there was a paper that we read where they used a VQVAE to do image generation or generative image creation. Several recent advances have opened the door for much better image generation performance. One is contrastive language image pre-training, CLIP. Okay. jointly training image and text. In addition to CLIP, the toolkit of generative models has recently grown. Large language models encoders have been shown to effectively condition image generation on long natural language descriptors rather than just a limited number of preset categories of images. Significantly larger training data sets of images and accompanying captions have improved overall performance. All of these factors together have given rise to a range of models able to generate high-resolution images with strong adherence even to very detailed and fantastical. So yeah, image gen is kind of the Google version of Stable Diffusion. Yep. They haven't released it though. Can't use it. Sad. Increasing the size of the language model in ImageGen boosts both sample fidelity and image text alignment much more than increasing the size of the image diffusion model. Yeah, so this is kind of the whole bitter lesson thing all over again, right? Where the larger you make these language models, the better everything happens. So largely, we're just sitting around waiting to have bigger and bigger language models, and everything else is kind of a waste of time. Work offers several advantages, including a new memory-efficient UNet and a classifier-free diffusion guidance. Yeah, this is we saw this over and over again. Like all the diffusion papers have this now, where they drop out and they have this like guidance score or guidance weight. Guidance, a cheat code for diffusion models. Okay, it's a nice little blog post that explains that. That could be cool to read. Party uses auto-regressive transformer architecture to generate image pixels based on a text input. Encoder-based vision transformer is shown to significantly improve the output of a vector quantized GAN model. Yeah, this is the one that I think we read. Where much better results are obtained by scaling the transformer encoder decoder to 20 billion parameters. Perhaps not surprising, given that its language model Party is particularly good at picking up on subtle cues in the prompt. Yeah, so this is kind of like everyone's seen this now, but like you can generate pretty good images with like kind of crazy prompts. All right, user control. The advances described above make it possible to generate realistic still images based on descriptions. However, sometimes the text alone is not sufficient to enable you to create what you want. E.g., consider a dog being chased by a unicorn on the beach versus my dog being chased by a unicorn on the beach. So we have done a subsequent research in providing new ways for the user to control the generation process. In Dream Booth, users are able to fine-tune a trained model like ImageGen or Party to generate new images based on a combination of text and user-furnished images. Yeah, so I think there's a couple startups that are actually kind of doing this as well, where you can provide a couple images of your own face and then use Stable Diffusion or kind of a generative model. I don't know if it's actually Stable Diffusion to basically generate images where you're kind of the central part of the image. Yeah, allow users to place themselves into generated images. Yeah, so you give the model a couple pictures of yourself here, or in this case, your dog, and then when you say a dog in the Acropolis, it'll actually use a dog instead. This is very likely going to be a Google product that's available very quickly. One of the next research challenges we are tackling is to create generative models for video that can produce high resolution, high quality, temporally consistent videos with a high level of controllability. Unlike images, where the challenge was to match the desired properties of the image with the desired pixels, or generated pixels, With video, there is the added dimension of time. Not only must all the pixels in each frame match what should be happening in each video in the video at the moment, but they must also be consistent with other frames, both at the very fine grain level, but also at the coarse grain level. This year, we've made quite a lot of exciting process through to image gen video and Fnacky. So yeah, the videos are still very primitive, like the generative videos, but they are getting better. I think this is more going to be to me, this is where GANs were in like 2014. So I think video generation will be more of a thing kind of in the later 2020s, like 2028, 2029, and so on. So the way they're doing it now is kind of very small, right? 16 frame video at 40 by 24, and then it just like super resolution. Yeah. And it uses the super resolution model to upsample. So this other one here, Fnacky, introduces a new transformer-based model from Lydio for learning video representations, which compress the video to a small representation of tokens. Text conditioning is achieved by training a bidirectional transformer model to generate video tokens based on the text description. Generated video tokens are then decoded to create an actual video. Because the model is causal in time, it can be used to generate variable length videos. This opens the door to multi-prompt storytelling as illustrated in the video. Teddy bear keeps swimming under the water with colorful fishes. A panda bear is swimming. Generative audio. In addition to visual-oriented generative models, we have made significant progress on generative models for audio. In Audio LM, a language modeling approach to audio generation, and the accompanying paper, we describe how to leverage advances in language modeling to generate audio without being trained on annotated data. Using a language modeling approach for raw audio data instead of textual data introduces a number of challenges that need to be addressed. Yeah, raw audio data is actually very hard to deal with. A lot of people, like one thing that I've seen done is people will basically take the audio and turn it into a spectrogram, right? So spectrogram, this stuff, right? They'll turn it into this, and then they'll use like a convnet or some kind of like image-based model. So I don't know what the state of the art for audio generation is, but longer sequences. Audio waveform typically contains hundreds of thousands of values. There's a one-to-many relationship between text and audio. To deal with this, we separate the audio generation process into two steps. The first involves a sequence of coarse semantic tokens that capture both local dependencies and global long-term structure, while heavily downsampling the audio signal to allow for modeling long sequences. Yeah, so it seems like kind of what they're saying here is that, right, with transformers, the size of the input sequence kind of determines how much compute you're going to use, because the attention mechanism squares quadratically with the size of the input. So the difficult part about audio is that you're sampling at a very high frequency, so the overall size or overall length of the audio sequence is actually huge. So figuring out how to kind of like compress that or kind of subsample that is very important. So that's kind of what they're doing here. They have like a kind of like a global one that's probably downsampled, and then a short-term one. Rely on a portion of the model that can use a sequence of coarse tokens to generate fine-grained audio tokens. Audio LM generates syntactically and semantically plausible speech continuations while also maintaining speaker identity and prosody for unseen speakers, right? Prosody is the rhythm and tone, as we just say. Concluding thoughts about generative models. 2022 has brought exciting advances in media generation. Computers can now interact with natural language and better understand your creative processes and what you might want to create. This unlocks exciting new ways for computers to help users create images, video, and audio. in ways that surpass the limits of traditional tools. This has inspired more research interest in how users can control the generative process. Advances in text-to-image and text-to-video have unlocked language as a powerful way to control generation, while work like Dreambooth has made it possible for users to kickstart the generative process with their own images. 2023 and beyond will surely be marked by advances in the quality and speed of media generation itself. Alongside these advances, we will also see new user experiences allowing for more creative expression. It is also worth noting that although these creative tools have tremendous possibilities for helping humans with creative tasks, they introduce a number of concerns. They could potentially generate harmful content, blah, 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 audio content. I don't know. I think this is all bullshit. Like, to me, the companies, when they start telling you that, oh, these models can be dangerous, right? Like, really, this is just a way for them to justify kind of authoritarian control over the AGI, right? Something to think about. But he uses this as kind of a segue into this section here, responsible AI. So in this section, he's basically generate misinformation, right? They can also be used to generate harmful imagery. Leaders in ML and AI must lead not only in the state-of-the-art, but also in state-of-the-art approaches to responsibility and implementation. Model and data cards. So having an idea of what this model was trained on, what it's not good at, what it is good at. This stuff. So a lot of like models are trained on kind of Western data sets, so they're kind of going to be better with English. They're going to be better with lighter skin tones. Our responsible AI approach includes the benefits users and societies, intentionally apply AI principles, responsible approaches to access and externalization. Like, what? I don't know, Google, like, you know, like at the end of the day, like, OpenAI allowed people to play with DALL-E, but Google did not allow people to play with ImageGen. So, is that responsibility? Is that what responsibility is about? Is not letting people use things? Seems like that's more a money grab, right? Listen, learn, and improve based on feedback. Can't have feedback if you don't let people use things. Regular reviews. Stay on top of areas of concern and risk. Lead and help shape responsible governance. Help users and society understand what AI is. Yeah, so I think it's kind of like, this gets into almost like a political nature, but to me, I think this is like, right, like whenever you had the whole terrorism scare in the early 2000s, and now anytime you go through an airport, you have to basically get scanned with this machine, right? And it's like, well, we have to protect people against terrorists, so now that's why we're scanning everybody, right? But it's like, is the scanning about protecting terrorists, or is it more about the government kind of knowing what everyone's doing? And I think there's kind of a similar thing here where you have people who mean well and they want AI to be used to benefit society, but the problem is that they will create a bunch of centralized power in order to do that, and then people who have malicious intent will then use that centralized power to benefit their purposes, right? So it's kind of one of the fundamental problems here, is that like preventing people from doing evil creates a set of tools that allows people to do evil. Okay, concluding thoughts. We're excited by the transformational advances discussed above, many of which we're applying to make Google products more helpful, including Search, Assistant, Ads, Gmail, Maps, YouTube, Workspace, Pixel, Nest, Android, and Translate. So they're going to really try to put these, put AI technology into every single one of their products. Thanks to our invention of the transformer model and advances like sequence to learning, people can have a natural conversation with the computer. Yeah, I think this is kind of what I was saying before, where they're kind of attributing too much to the architecture and not enough to the data set. The reason we have good AI right now is because we have been creating a data set, a giant public data set, which is the internet, for decades, right? The advances in AI are because the internet is a huge amount of public data. The transformer itself is actually not that important. I don't think that the transformer model is really doing anything, and I think that it is somewhat important, but it's like it's not the transformer that is leading to these advances. Thanks to new advances in generative models, computers can help people create images, videos, and audios. Combined with advances like natural language, computers can understand what you're trying to create. Another transformation changing how people interact with computers is the increasing capabilities of multimodal models. We are working towards being able to create a single model that can understand many different modalities fluidly, understanding what each modality represents in context, and then actually generate different modes in that context. So a single language model that has every single task in it, right? Hundreds of languages, vision, speech. On-device multimodal models. I might have to read this. Like, how are they actually fitting these models into tiny little devices? New advances in AI present an exciting horizon on the ways computers can help and people get things done. Will enhance or transform our long-standing mission to organize the world's information and make it universally accessible and useful. Yeah, this is kind of what I was saying, where they've changed their mission a little bit. They've changed the wording on it. Today, what excites us is how we're applying many of these advances in AI to enhance and transform user experience, helping more people better understand the world around them and get more things done. Awesome. All right, so that was a nice little article there by Jeff Dean on kind of the different stuff that Google Research has done in 2022 and kind of where they see the puck going in 2023. So I think, to me, maybe if I had to make some calls, I think Google comes out with its own kind of chat GPT. They put it directly in the Google search. I think you see some kind of image gen, like something like this, right? Where you can pick your own, it looks at your own images in Google Photos, and then you can kind of like create images of yourself in various situations. So this will be kind of integrated into Photos. I think the video stuff is still far away, but the language-based interaction is also another thing. Like, right, you could kind of, there'll be like a language mode for Google Maps, where rather than kind of typing things in, you can just kind of talk to it. So I think maybe those are some things I could see in 2023 in terms of like actual hard products. And yeah, in the beginnings of prompt engineering here, right? So like there's a kind of a scientific discipline which is being created, which is basically, I think, a successor to human computer interaction, which is basically prompt engineering. And it's how do you create prompts? How do you ask questions to these AGIs in such a way that they give you the. So yeah, that's it. Thanks for watching the stream. I have a bunch of work to do this week, so I might not stream every single day. I'll try to stream at least 3 days. I'll probably do Monday, Wednesday, Friday, or Monday, Tuesday, Friday, or something like that. But yeah, thanks for listening, and see you guys later.